Hi there, I'm Tori Stenmark with the Geek Girl Con Do-It-Yourself Science Zone, and I'm here to show you how to do at-home paper chromatography. We're going to separate out the different colors in mixtures such as ink or dye or food coloring. All of the colors that you see are made up of a bunch of different molecules working together to create the color and to make it stick to paper, to make it safe to eat, to do all the things that it's going to do as a food coloring or an ink. But we're going to separate out those individual colors so you can see what goes into them. So we can see that green is a mixture of blue and yellow, or that purple is a mixture of red and blue, things like that. So here's what you're going to need for today's experiment. A coffee filter, you can use these conical shapes or the flat basket shapes, whatever you have, scissors, pencil and a ruler, something to separate out the colors of. I've got some food coloring, you're going to need a plate and some toothpicks if you want to use food coloring, or you can use markers, pens, Sharpies, anything like that, anything that writes with color, with some kind of ink or dye or pigment. You're going to want a stapler. And then the last thing you're going to need is a straight-sided jar or glass with a little bit of water in the bottom of it. We're going to start with our coffee filters, and we're going to cut them to be big rectangles. So first I cut them open, and I'm going to want to make it sort of the best rectangle I can. It doesn't have to be perfect, but we're looking for something that's approximately a rectangle here. So when you open up, you have more or less a rectangle. If you've got a different shape of coffee filter, you'll cut it differently, but the principle is the same. Nice big rectangle. You're going to take that, you're going to use a ruler and a pencil, not a pen. You're going to start with a pencil to mark off a line roughly 1.5 centimeters from the bottom edge. Doesn't have to be perfect, I just want to know roughly where I'm starting from. On that line, you're going to put little tiny dots of everything you want to test. So, in this case, I have a number of different pens and a little Sharpie here. So I'm going to make a little dot right on that line, spaced out, with my markers. Underneath that dot, in pencil, I'm going to label it with what it is. So that one is Sharpie. Now the reason that I use a pencil is that the color in a pencil isn't an ink. It's not going to separate through this process. It's going to stay right where we left it. So I'm just going to draw and label little dots. So I've got my 4 inks marked out over here. On the other half of the piece of paper, you can also do this on a second piece of filter paper, I'm going to indicate with food coloring. Now food coloring is a little different. If I try to squeeze out some food coloring from one of these dropper bottles, it's not going to go super well. There we go. If I try and squeeze something out, I'm going to get a big massive blob everywhere and it's going to make a big mess. So I don't want to do that directly on the paper. Here's what I'm going to do instead. I'm going to grab a clean plate. You can use a paper plate or a plastic or a ceramic one, and put a little drop on the plate. Now I can use a toothpick. Dip the toothpick in and get a teensy tiny bit of food coloring on the end of that toothpick, and then put that on my paper. Because if I put a whole big dot of just big old drop, it's going to be way too big. It's not going to work very well. So I'm going to do that, and I'm going to label that. So we call this process spotting, where you make a little spot of your compound on the plate here. So I'm just going to dip the very tip of my toothpick in my sample, just get a little tiny bit of it on there, and then just touch it real quick to the paper. I'm going to go and touch it like 2 or 3 times in the same spot. Dip. And I have a very, very tiny little dot right there of my blue food coloring. I'm going to use a few different colors, and I'm going to label each of those separately. Because what I might think, well, that's very easy to distinguish right now, is going to get a little harder to distinguish after I've let this experiment happen. And I think the last color I want to try is a red here. You can do as many or as few colors as you want. However many will sort of fit nicely on your piece of paper with a little bit of space between them. You want to give your paper a little bit of time to dry. If you look at it and any of your little dots, your spots look wet, give them a moment or two to finish air drying. The amounts we're using are pretty small, so it should evaporate, should dry pretty quickly. So now here's our start. You might want to take a picture of this or make a sketch of it, or just generally remember that you've got all these different colored dots down here at the bottom. Now what we're going to want to do is curl the ends together, staple them. If you can, staple them so they're not actually touching each other, so it's just the staple holding them together, like this. You're going to want to do that at the bottom and at the top. It can be a little tricky. If they do overlap a little bit, that's okay. But sort of aim to have them not quite touching. There we go. So now I have a little cylinder with my dots on it. The cylinder, we're going to get wet, and we're going to allow the water to separate out my individual color molecules. That's what this jar with a little tiny bit of water in the bottom of it is. Now what I want to make sure is that the amount of water in the bottom is less than the height of the line we drew in here. So you can actually stick a ruler in there if you want. You can just kind of hold them up next to each other, but it looks like I'm in good shape here. So just a little bit of ordinary tap water in the bottom of that jar. Or glass, whatever you've got that's sort of tall and vaguely cylindrical like this. You're going to take this with your ink dots towards the bottom, and you're going to slip it inside there. You don't have to screw the lid on, you can just set it on there, and then you're just going to wait. What's happening as it stands is that the color molecules in the ink, or the food coloring, are going to stick to the paper. They're also going to be attracted to the water. The water moves up the piece of paper through something called capillary action. That's how paper towels work. If you set down a paper towel, it kind of sucks all the water into it. That's capillary action. And our filter paper here is doing the exact same thing. As the water moves up, some of the color sticks to the paper, some of the color dissolves in the water and moves with the water. It's going to kind of stick to the paper again, it's going to come off, it's going to move with the water and kind of go back and forth like that as the water travels. Some particular colors will stick more to the paper. Some colors are going to stick more with the water and they're going to move more. So what we're going to see is a separation. We're going to see some colors sticking to the paper more and being down close to where we left them. Some colors are going to travel with the water and they'll actually see them move up the piece of paper. They're going to separate out. That's called chromatography, which is a word that originally means to write with colors. The way we use it now is as a separation between multiple different substances here. So you're going to just sort of let this travel until the water gets close to, but not all the way up to the top. You don't want to let it run all the way off the top of it because then you won't be able to see how clearly everything traveled. So it'll take a few minutes. I'll give it a couple more minutes here. But actually, I think we're pretty much set. So you're going to reach in and just pull that sucker out. And you can see that my compounds have moved. Almost all of them, in fact, have separated out. Looks like the Sharpie didn't. All right. So what I'm going to do now is I'm going to go ahead and undo the staples. I'm very careful because it's wet and therefore delicate. I'm just going to sort of slide it off those staples. Open it out. And now we can see all of them at once. And you can sort of let this dry somewhere, put it someplace where the water won't harm it. And we can see a lot of things have happened, right? Here's my finished and dried paper chromatogram. And we can see that a number of these have run out and separated in a variety of different ways. So if we start over here on the left, here's our Sharpie marker. It hasn't changed at all. It's still standing there pretty much exactly the same as it was. And that's because a Sharpie, it says right there, is a permanent marker. It doesn't dissolve in water. It's not going to separate through a water-based method. So here, it's not going to change. Next to it, I've got a couple of my fancy fountain pen inks. Habanero here is orange. It's separated into pink and yellow. We can see that the pink mostly stuck. A lot of it's down here where we started, and it's sort of gradually smeared its way up the piece of paper. But the yellow has moved much further. The yellow spent more time dissolved in the water, so it traveled with the water more and moved further up the plate here. So it's traveled all the way up and it's separated out from the pink. Together, we have that orange color. Here's my Caribbean blue here. Now, it looks like I got a little bit of contamination on this piece of paper because I think that this dot and these bits over here were ink added later that wasn't supposed to be there originally. Because what I think I'm seeing is that the blue pretty much goes all the way up to the top and doesn't really separate much. It streaks a little bit, it doesn't all move together, but there don't seem to be many other colors besides blue. Not like this nice black here. So the ink, to begin with, is black, but when you see it separate out here, we've got a really interesting color mixture. We've got plenty of gray down towards the bottom and it's sort of all along, but up at the very top here, I've got, looks like pink, orange, blue or green in there, maybe all of them. Because black is a color that's usually a mixture of a bunch of different colors. All together in one dot, they look like black, but when we use paper chromatography, we can separate them out and see separate individual spots. Then over here on the right, I have my 3 food colorings. I have blue, which is pretty much just blue. Red is pretty much just red here, but this purple is really interesting because the purple has cleanly separated into a pink and a blue color here. Where the pink stays down, the pink is more attracted to the stationary paper, whereas the blue is more attracted to the mobile water, and the blue moves further out. And in fact, the package of food coloring happens to tell me exactly what's in it. Here, neon purple contains water, propylene glycol, those are the liquids that make it a liquid, FD&C red number 3, FD&C blue number 1. Propylparaben is another carrying agent. So we've got our red down here, right? There's our red. We've got our blue up here at the top. So they separate out differently because it's a mixture of different substances, like so. And we can also compare that. I've got a piece of paper that I haven't run yet. So I've spotted it, I've loaded in my samples and made my little dots of ink, but it's not been run yet. So we can compare those original tiny little dots to what happened after we've let it run, after we've let the water travel past it. Here's that orange for habanero, separates to our pink and our yellow. That single dot of purple separates out to these 2 compounds here. And if you want to try other things, feel free to try anything and everything that's an ink or a pen, again, food coloring, pretty much anything like that. I've sort of made some suggestions of things that should work here, but basically anything that makes color, you you can try it and see if it works or if it doesn't. If it doesn't work, you've still learned something. You've learned that doesn't separate. You can also try different solvents. So I've used water here, but you could also try if you've got a source of things like acetone, or rubbing alcohol or ethyl acetate, anything like that. There's a bunch of different solvents you might have access to. Make sure you're being very careful and safe with those because they can be a little more dangerous than water, but things will travel differently with rubbing alcohol than they will with plain water. So you can experiment with that too. This has been Paper Chromatography with Geek Girl Con's Do-It-Yourself Science Zone. Have fun, learn some stuff, and stay safe.
The following demonstration was recorded outside in a beautiful park by Stacy Tiedegan and her assistant Molly. Stacy is wearing her NASA baseball cap and will show us how to make a plastic bottle into a rocket ship.
We're going to the moon in 2024 with NASA's Artemis program. But in order to get there, we need rockets, which allow us to escape Earth's gravitational pull. Hi, I'm Stacy Tiedegan, and I'm the Outreach Coordinator for the Planetary Science Division at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And today we are going to be launching some rockets. But instead of using liquid hydrogen and liquid oxygen, we're going to be using water and a 2-liter bottle. So you will also have a bike pump, which when you're pumping the bike pump into the liter bottle, you build up enough pressure that the rocket actually launches, and you get to launch your own water bottle rocket without using really expensive equipment. So to launch a water bottle rocket, you need a few supplies. One of the most important things is safety goggles. You gotta wear your safety goggles. Second thing, you're going to have some water. So water is going to be your source of fuel in your water bottle rocket. And then you want a 2-liter bottle, and then something on the end for a nose cone that adds weight. So I have a tennis ball wrapped around with some duct tape, but you can use Play-Doh or whatever you have available at home. And then you want to make your fins. The purpose of your fins is to stabilize your rocket when it launches. So I made my fins out of cardboard, but you can make it out of foam board or poster board or whatever you have at home. So another thing you're going to need is a bike pump. So the bike pump will allow you to pump in air into your 2-liter bottle to build up enough pressure so that your water bottle rocket will launch. And then we want a cork. So a cork doesn't come with a hole in it, but you need to make a hole in it by using a nail. So you'll insert the nail in the center, and then you can pound the nail in with a hammer. Make sure an adult is with you for this part when you're poking a hole in your cork. You don't want any injuries. You might need to use a hammer to pull your nail out of your cork. So when you're making your hole, the goal is to make sure that your hole is thick enough around that your bike pump needle can pass through it. So next we're going to add some water as our fuel source to our liquid water bottle rocket launching. And I have an assistant here to help me pour the water in. And this is Molly. Awesome. Molly, pour it. And we're going to pour it until it reaches this little lip of a soda can. Alright. Wait, stop. Go ahead. Oh, keep going. Okay, lots of fuel. Lots of fuel is important. Makes it go higher. Keep going, you're almost there. And stop. Thank you very much, Molly. You're welcome. Next, we need to plug our water bottle rocket using our cork that we put a hole in earlier. Do that. Make sure it's nice and snug. Okay. And then we want to attach our little bike pump nose piece. And now we're ready to go launch our water bottle rocket. So now we're going to attach our bike pump hose to our bottle, making sure it's nice and secure, like so. So we want to make sure our water bottle rocket is pointed up straight and not sideways. You want it to launch straight up. And just as a safety reminder, we gotta make sure we're wearing our safety goggles, okay? Alright, are we ready to launch another water bottle rocket? Alrighty. Molly, count down for 5. 5, 4, 3, 2, 1. Yay! Delayed. Now you can launch your own rocket, just like NASA.
Dr. Gwen Pearson is in her lab wearing a dark blue lab coat, long blue hair adorned by butterflies. She will explain how insects cosplay just like the rest of Geek Girl Con.
Hello, I'm Dr. Gwen Pearson and I'm here in the Purdue Bug Barn. This is where we keep all of our insects in the insect zoo. One of my favorite parts of Geek Girl Con is cosplay. I love dressing up. It's super fun to dress up and pretend. For some of my insect friends here at the Bug Zoo, every day is cosplay day. This lady has a really cool green suit that helps her look like a leaf. And look, she's even shaped like a leaf. Here's that same insect on leaves that she normally eats. Can you still see her? Look at how well she hides. She looks just like a leaf herself. You can kind of see her face. I'll have to move this little leaf here. There she is.
So, why do you think these animals are pretending to be something that they're not? Insect cosplay helps caterpillars like this hide from predators that might want to eat them. Animal that eats other animals is called a predator. Usually when we talk about predators, you're thinking about lions and tigers and bears. But honestly, this tiny little bird, pretty ferocious little predator. You can see that it's got keen eyesight and it's always looking around for a meal. It's especially important in the spring that bluebirds catch enough insects to feed their babies. And if you're a plant eater, one of the easiest ways to hide is to dress up like a plant. This caterpillar has disguised itself so well, it's hard to tell where the caterpillar begins and the leaf ends. If you couldn't see its little chompers eating, you'd probably never even notice it. If you happen to be on a tree trunk, you can really blend in. This is a caterpillar, really. See the little fluffy feet? And this is a caterpillar, and it basically looks like a stick sitting on a stick. You can also see its little fluffy feet. If you were a hungry bird, I bet you'd never see this katydid. Her cosplay is so good. Group cosplay is a really fun way to pretend with your friends. Because bees and wasps wear similar outfits, their cosplay helps reinforce a message. Do not pet! In fact, the black, red, yellow, orange stripy combo is so common, humans borrow it. We put it on things that we think are dangerous to warn everybody. Deadpool is a great example of warning coloration. Black, red, yeah, you don't want to make him mad. It's not going to end well. Monarch butterflies and caterpillars use the same yellow, black, orange stripy pattern to send a message. You should not eat us. In fact, if a bird eats a monarch caterpillar, it's going to barf. They get their vomity chemicals from the milkweed that they're eating. The butterflies' bright colors are a reminder to leave them alone too. And now it gets a little meta. If you're harmless, but you want to be scary, you can dress up as something scary. Yellow, orange, black stripes? This is a wasp, right? Nope, it's not. It is a moth. It is completely harmless and can't bite or sting. This moth even got rid of some of the colors and scales on its wings to look more like a wasp. Pretty amazing, huh?
Black and yellow stripes, it's eating pollen? Nope, it's not a wasp, it's not a bee, it's a fly. If you look a little closer, you can see it has only one pair of wings and kind of weird mouth for something that's pretending to be a bee. Here is a fly that's cosplaying as a wasp and a real wasp. Can you figure out which one is which? Yep, the one on the right is the one that's wearing a costume and pretending. The real wasp is the insect that's on the left. So we've seen insect cosplay working in a whole bunch of different ways. You can hide, you can let everybody know you're really dangerous, or you can fake predators out so you don't get eaten. Why don't you give insect cosplay design a try? There's a link to a handout that you can download, or you can just draw on your own paper. Invent an insect and then design a costume for it that helps it not be eaten, or that maybe advertises that it can sting or bite and you should leave it alone. Decide what their homes look like and what eats them. Have lots of fun and be creative as you want. This is your insect, you're inventing it. Then you might try going outside and see if you can do the same thing for a real insect. See what you can find and figure out.
Geek Girl Con Photo Booth 2015 credited to Joshua Weiner. Miscellaneous insect footage or personal footage was licensed by Via Canva. Deadpool Group Cosplay CC2 by Is2Let the TV/Flickr. Fly Wasp Mimic photos from Insects Unlocked and amazing insect photos were used with permission from John Horstman. The following demonstration features Dr. Addie Kingsland wearing a pink headband with unicorn ears and a horn, pink hair, glasses, and a pink lab coat. They will show us how to make a raw egg bounce.
Hey there, GGCers. Would you believe me if I said I could make an egg bounce like Pinkie Pie? Let's find out with science. You can do this at home. You just need a few supplies. A jar or cup, glass works best, some vinegar, and, most importantly, a raw egg. Carefully put the egg into the cup and cover it with vinegar. What do you see happening? Vinegar is an acid, that's why it tastes sour. It reacts with the calcium carbonate in the eggshells, which makes carbon dioxide, which is the same thing that makes soda fizz. Now for the hard part, waiting. Let's wait 24 hours. Do you see the film on top of the vinegar? What do you think that is? Let's carefully wash the egg to remove any remaining bits of shell. Are you ready to find out what happens when I drop it? What do you think will happen? It bounces! What other liquids in your house do you think would do this to an egg? Water? Milk? Orange juice? Oil? Write down some predictions, do some experiments, and tell us the results.
In the following demonstration, scientist CJ will show us about diffusion in the kitchen using Skittles, a clear plastic bowl, and different liquids.
Hello, Geek Girl Con. Today we're going to talk about science with Skittles. And what you're going to need to do this experiment is you're going to need a bag of Skittles. I like the original kind. It's very colorful. You're going to need a round bowl. So there's a, you can use any sort of round bowl you like. I have here a clear glass round bowl, and then you're going to need some water. So we are going to add this water into this bowl, and we are going to see what happens. And those of you who are watching this video probably are Skittles experts. And what you know about Skittles is that they have food coloring on the outside. And that food dye on the outside will dissolve in water. And that's why the food dye gets on your tongue when you have some Skittles, and you can open your mouth and look and you can see you have a red mouth. And what you're seeing here is that the dye is diffusing. It's a big word there. The dye is diffusing from the outside of the bowl to the inside of the bowl. Diffusion is when molecules go from an area with a high concentration to a low concentration. So they went from the outside of the bowl, where there is a lot of the dye, to the inside of the bowl, where there isn't very much. And this happens in this weird, random, wiggly way that molecules move. And they tend to move towards a part of an area where there isn't a large concentration. So something else that you can see and that you can do at home is that you can see what happens with temperature and diffusion. So we have two more bowls here, and then we have hot water on the left and we have cold water on the right. And so we are going to find out what happens when we add hot water and cold water at the exact same time to two different bowls. So you have an opportunity to be a scientist and make a prediction. So you can say, well, will it be the hot water that will have the faster moving colors, or the cold water? And so let's find out. So you can make your prediction. You ready? You're thinking about it? All right, I'm about to add in 3, 2, 1. And what you see is that the water is diffusing much faster with the hot water than it is with the cold. And that's because the water molecules themselves have a lot of energy because they're hot and they're wiggling, and that water is moving. And so the one on the left is basically already done, the hot water one, and the cold water one is still just getting started. In fact, the molecules on the right side, you can see, haven't quite yet diffused to the center of the bowl until right about now. That's actually a really lovely one. Really nice colors. So you can see what happens with all different kinds of liquids. So hot liquids, warm liquids. You can that one's really pretty. You can work with your mom to find what liquids you have. We have in our house, we have some seltzer or some sparkling water, and we are going to give sparkling water a try. What do you think will happen when we add in the sparkling water? We'll find out. Will it act the same way? Will it be different? What will the effect of the bubbles be? Let's find out. This is the best part about science, is looking at a system and then making a change and seeing what's going to happen. And what we see is that, well, it basically acts like all the other ones. That yes, there are some bubbles, there's still bubbles in the bottom, but it's still diffusing like you would expect from the area of high concentration to the area of low concentration. So that's another liquid. We have another weird liquid here. It's pretty common. It's called light corn syrup. So that is something that we often use in cooking. If you make pies, that sort of thing, you may use some light corn syrup. Light corn syrup has about 40% water. And here are 2 Skittles that have been in light corn syrup for about 20 hours. And what you can see is that the color really doesn't diffuse off. It's pretty remarkable that the dye isn't very interested in dissolving in the corn syrup. It's not diffusing very much at all. So just to prove to you how difficult it is, we're going to walk over here to So here we are at the microwave. We're going to take the corn syrup. It flows very slowly. And we are going to heat it for 30 seconds. And
Is it okay if I pause it?
And that corn syrup will get pretty hot. And we'll see what happens when we add the Skittles to the corn syrup. What do you think will happen? Do you think that it will dissolve right away or that it won't dissolve at all? There's only one way to find out, and it's to do the experiment. So the corn syrup is really hot. This is something, if you're going to do this experiment, this is something that you're going to want your mom and dad to help you with. So we are dropping in the Skittles. They're down in the bottom, and you can see that it's hot enough that there are bubbles forming from the boiling. But what you don't see is you don't see the molecules diffusing through the water. In fact, it's really not doing much at all because the corn syrup just isn't very soluble, or the Skittle dye, it just isn't very soluble in the corn syrup. Not even with heating. Well, thanks for doing Skittle Science with us, Geek Girl Con. We'll talk to you later. Bye.
In the following presentation, a book reader, professional chair-sitting cat, space pirate, scientist spouse, and an alien specialist all come together to teach us about SpaceTime. Make sure you don't miss the special guest.
Oh, good evening. I was just reading this book, Einstein's Unfinished Symphony. It chronicles the conception and development of the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. It's a special observatory. It was created to put one of Einstein's most extreme predictions to the test. It doesn't look for light like other observatories. No, it looks for ripples in the fabric of space-time. In addition to inventing calculus, Sir Isaac Newton was one of the first physicists to provide a detailed explanation for the phenomenon we know as gravity. And despite referring to it as an inexplicable, mysterious force, his explanation served us well for about 200 years. But in the late 19th century, the physics community started noticing holes in his theories, scenarios in which Newtonian mechanics did not suffice. It wasn't until 1915, when Einstein published his theory of relativity, that he proposed that space and time were actually the same thing. Not only that, but that they formed a fabric, if you will, that held reality as we know it together. Like any fabric, it could be bent and warped. And it went on to say that these distortions were caused by objects of large mass, and that gravity was not a force, but merely a consequence of that mass bending space-time towards it.
Hey guys, to start things off, let's check out this demo about flat spacetime. The black mesh surface you see here represents spacetime. Spacetime is essentially flat in the absence of gravitational sources. An example of a gravitational source would be a large collection of masses or a large mass like the Sun, for example. Away from any gravitational sources, spacetime can spread out and is essentially flat. We can see that demonstrated here as the billiard ball rolls across the black mesh. Without any significant curvature in the fabric, the ball is free to move along in a straight line at a fairly constant speed. This motion is consistent with Sir Isaac Newton's first law that an object in motion tends to stay in motion. And what he really meant by that was that an object will continue on its existing path at its existing speed until some external force interferes. But what Newton related to as a force, Einstein proved was something else entirely. Now in this next video, what we see is a massive object in the center of the table, and this mass has warped the shape of the fabric on which it sits. We could say that it has produced a well around it, and we can see how the sides gradually slope downward toward the ball. This is a good analogy for how mass warps space-time. We can see that as an object approaches, instead of falling along its path in a straight line like in the earlier video, it encounters the curvature produced by the ball, and that curvature manipulates the path the marble takes. The marble has fallen into this well and is stuck, riding along the edges, orbiting the ball to the center.
As other masses traveling through space come close enough to this center mass, they experience the effects of its space-time curvature. You can see they begin to circle it just as the planets in our solar system orbit the Sun. The main difference, of course, is that there is a decent amount of friction between the sheet and the marbles, which causes them to slow down and spiral inwards pretty quickly. Comparatively, the planets in our solar system experience no friction in space and actually move slowly away from the Sun. As the Sun burns its fuel, its mass and gravity decrease, a result of the curvature of space becoming more shallow around it. If you've ever sat outside at night, you've probably noticed that big yellow moon moving across our sky. But if the Earth orbits the Sun, why doesn't the Sun pull the moon away from it? Well, let's take a look. As we can see in this demonstration, the planet that the moons are orbiting produces its own curve in the space-time around it. It's just deep enough, and the moons are just close enough that they ride that smaller curve while the whole system rides along the curve from the Sun. Then, as they get closer to the center, because of the friction of the sheet, we can see the moons get ripped from the planet as they fall into the gravity well formed by the Sun.
Finally, let us consider a galaxy. What you might not know is that galaxies have an overall rotation to them. Now, how this came to be is what we have our very own alien specialist here for.
This, my friend, is a magnificent question, and the answer must clearly lie within the stars. But to me, this just screams extraterrestrial intervention, right? Well, let's have a look, and this time how about we play the aliens, and this time we introduce some chaos. Let us introduce many sets of marbles, each with a unique starting orbit direction and speed. Watch closely here, as otherwise you might miss what happens to chaos over time. You see, no matter what direction the marble moves in initially, there will always emerge order. Order in this case is the orbit of all remaining marbles in a unified direction. So, you see, from chaos became order, and that is what we see today. When we consider a system such as our early universe, where chaos was part of everyday life, well then its natural next step would be order. And that's what we see. That's what we see when we point our telescopes to the sky and we see rotations and we see orbits. That is what we see. Well, I suppose this doesn't prove the existence of extraterrestrial life.
It's false. No way. Not this time. We created it. Not this time. No, not this time. It's totally made up.
But what it does prove is that Einstein's theories that he set up so long ago actually make sense.
The space-time demo shown in this video can easily be created at home. In order to create one, you will need the following: a rubbery or stretchy fabric, like the tablecloth shown in this video, a hula hoop or other circular object with an open center. In this video, we used PVC pipes to create a circle. Binder clips, tape, or other strong methods of holding the fabric over the circular opening. Binder clips are nice because they're temporary. Finally, some spherical balls with enough weight to displace the fabric when placed on it. Once you have these materials, simply stretch the fabric across the circle and attach it to the sides of the circle using the binder clips or other materials. For the best results, the fabric should be taut and flat when nothing is placed on it. I encourage you to experiment with different types of setups like the ones shown in the video, as well as others that we haven't showcased.
In this demonstration, Dr. Stephen Granata, along with two silent adolescent assistants, will show us how to use Jell-O for optics in their kitchen.
Hi Geek Girl Con, I'm Stephen Grenade. I'm an optical physicist, and today we're going to make some optics. Now, optics work because different materials have a different, what we call, index of refraction, which is related to the speed of light. Light actually travels a little slower in material like water than it does in air. So if light is coming into or out of the air and into water, for example, then it gets bent as it travels through there. So if you have a material that is shaped like a lens, then it bends light and changes where it focuses, for example. That's how glasses work. If you're very nearsighted, like me, you can see how you get a magnifying effect because of the shape of the material in my glasses. Now, we normally make lenses out of glass and out of plastic, but today we're going to make it out of Jell-O. I've brought my minions in for us to show you the materials that you're going to need to make your own optics. You will need Jell-O or gelatin. I suggest the unflavored plain kind because it doesn't have any color. You will need a saucepan to heat it in. You will need a square or rectangular pan to cool it in and let it set up. And then you will need a laser pointer. We'll make the gelatin with half as much water as the box calls for. For the Knox gelatin, we'll use a 1/4 cup per packet. To figure out how much water and gelatin we need, take your container and fill it to a depth of about 1/2 inch of water, and then pour that water into a measuring cup. For my container, to get about 1/2 inch of depth, I need 3/4 cup of water, which means I'll use 3 of these packets. To make the gelatin, pour about half of your cold water into a saucepan on the stove. Take the packets and sprinkle them onto the water. Once you've done that, wait about 20 seconds and then pour the rest of the water on top. Turn the burner on low and start stirring. You'll stir until all of the granules have dissolved into the water. Now this next step can take 10 or 15 minutes, so you should totally get somebody else to do it for you. Once the gelatin has completely dissolved into the water, pour the gelatin into your container. Let it cool off, and once it's a little cooler, put it in the fridge to set up. Let it cool in the fridge for at least 3 hours before you start to work with it. Once the gelatin has set up, remove it from the pan. If it won't come out, put the bottom of the pan in hot water for about 10 seconds. And if all else fails, cut it free with a sharp knife, carefully along the sides. Now comes the fun part. Let's carefully cut some optics. On a cutting board or a cutting mat, put the gelatin. Now ours got a little soft because of the hot water, so I put it in the freezer for a couple of minutes to get it to firm back up. We're going to start by making a long rectangle. The reason that I'm using a sharp knife is so that I can get very clean sides on it. It's a little wiggly on the sides, but that's all right. I'll also make a prism. I'll do that by cutting a rectangle and then doing a 45-degree cut along it. We can also cut lenses by making curved surfaces. If the sides curve out, it's a convex lens. If the sides curve in, it's a concave lens. Now we need our laser pointer and a little less light. Because the index of refraction of the gelatin is different from the air around it, when my laser light goes in from the laser pointer, it bends. You can see how it goes in at one angle, bends that way, and then bends some more. And in fact, depending on the angle that I go through, I can get it to reflect back out this side. This is called total internal reflection. At a shallow enough angle, the light doesn't actually come back out. It's bent so far that it continues in. Remember the rectangle that I carved? It passes light all the way through it. You'll notice that because the ends weren't clean, it scattered a bunch of light. I'm going to try to clean those up. Now here's the cool part. Because of those total internal reflections, if I do this at a shallow enough angle, it still comes out that end instead of bouncing out here. This rectangle is acting like an optical fiber. Finally, let's take a look at the lenses. I'm putting the beam in straight, but the lens is putting the light at almost the same spot out there. It's focusing the light to a focal point about there. This is how glasses work if you are farsighted. But what about the concave lens? It does the opposite. It spreads the light out further. Instead of focusing it in, it spreads it out, so that beams that come in straight get spread further. Many optical systems use multiple lenses to get different focusing effects. Besides these lenses and shapes that we made, I've got a lot of gelatin left over. You probably do too. Try making different angles and different curves and see what it does to the laser beam. And when you're done, if you want, you can eat the optics. Blah. Or not. Flavorless. Thanks for making optics with me in the kitchen. Have a great rest of the con.